magnetic field due to a current element, okay? And this is Biot-Savart law. And you'll use this formula a lot. Magnetic field due to a current carrying element, or a current element. We use the word, we don't use the word current carrying element, we just use the word current element, and we'll understand what is that current element. This word is something new for you, just absorb it as of now. As soon as we get into the topic, it will become clear. Magnetic field due to a current element, okay? So far we have studied that a current carrying wire behaves like a magnet. That means a current carrying wire will be doing what? It will create a magnetic field, creates a magnetic field. Our job today is to understand the strength of this magnetic field, basically the magnitude as well as direction. How strong is this magnetic field? How strong is this field? This is basically our concept. And how strong is this field was actually found out by two persons, Biot and Savart. So it's called the Biot-Savart law. And they experimentally found it out. Experiment. Derived the expression. Is that clear? Still one thing is not clear. What is this meaning of the word current element? So let's see. Our job is something like that. This is a current carrying wire, and say this wire is carrying a current I in it. The wire is carrying a current I in it, right? Our job will be to bring this wire, position this wire on one plane, say this blackboard or this piece of paper, and then find a point P. And at that point P, what is the strength of the magnetic field that has been created by this, right? That is our quest. So let me just bring it a little bit on this side. So this is my current carrying wire. And in this current carrying wire, we will have one point P. I have located one point P. And I want to find out what is the magnetic field, what is the strength of the magnetic field at this point P. Now, in order to do that, we break this wire into very small pieces. Same integration funda, many small pieces. So what do? We take the wire, we'll take the wire and we will break it down to small pieces, and each of these small piece is actually called a current element. Now there is something special about it, otherwise why will we call it as a current element? It is called as dl, and there is a vector. It's a vector. It's dl and it's a vector. So that means it must have some magnitude. So it has magnitude, and the direction is the I's direction, the current's direction. Magnitude is how much? Magnitude is dl. Have you understood this? We will break down this wire into small components. Each of this component will be called a current element. So this current element will be haunting us a lot in this chapter. So let's take a small current element out here. Okay, let me say, let's say from here to here we have a current element, and this current element is dl, right? dl vector. And sir, how do you find out what is the direction of this current element? Well, to find out the direction of this current element, I would like to have a small tangent at this place, like this, okay? And my dl vector's direction will be exactly the direction on this tangent. The current is going upwards, so at this moment dl vector is pointing upwards. Is this thing understood and you're clear about this? Okay, so this is dl current, and then we say that the point P is at a distance, say r. The point P is at a distance r from this current element dl. Point P is at a distance r. This is r. Okay. Now r is also shown as a vector, and the vector is from dl to r. So write down two things. Consider a wire carrying a current I in it, and a small portion of the wire, and the wire is broken into small pieces. Each piece constitutes a current element. A current element is a vector whose magnitude is equal to dl, and its direction is the direction of the electric current at that particular element with respect to that element. We are supposed to find out the strength of the magnetic field. So there will be a magnetic field out here, and that magnetic field is dB. Magnetic field is also a vector. What is the strength of this magnetic field, as well as what is the direction of this magnetic field? Both we have to find out. So P is at a distance r, or you can say the displacement from dl to P. Displacement is the better word. The displacement from dl to P is r, denoted by r vector. Is this understood? Okay, and we'll have one more parameter out here. Let theta be the angle between dl vector and r vector. dl vector and r vector. Can you write these things on your own? Right? Consider a current element dl. So one is, we have a current element dl. We have a point P where we want to find out the strength of the magnetic field dB, both in terms of its magnitude and direction. dB is at a distance r and is represented by r vector is the displacement vector from dl to P, and theta is the angle between dl vector and r vector. Clear? So if you want to have a little bit of clarity, we are somehow like this. We are somewhat like this. It's like, this is my r vector, this is my current element dl, and this angle is theta, or something like this. Clear? Okay. Now this setup was done, and you don't derive. Biot-Savart law is not derived. The experimental findings are done. Okay. Now the experimental findings. There are actually 4 numbers of experimental findings, 4 experimental findings. Number 1, dB is directly proportional to dl. dB is directly proportional to dl, which means longer the current element, stronger the magnetic field. Longer the current element, stronger the magnetic field. Okay. The second one, dB was found to be directly proportional to I. So a strong current will contribute to a stronger field. Stronger magnetic field. Third, dB was found to be inversely proportional to the square of the distance. These are very common findings. See, if you are near to the wire, obviously the magnetization effect will be more. dB was found to be, so farther the point from the current element, okay, weaker is the magnetic field. 4 points. See, what all did we have in that diagram? Imagine we had a DL, we had a I, we had a R, and we had one thing more. Look at the diagram. Theta. Yes. 4. And we call this as dependence on angle or angle dependence. Dependence on angle. The dependence on angle is such that if theta is equal to 90 degree, if theta is equal to 90 degree, dB is strongest. And if theta is equal to 0 degree, dB does not exist. Okay. If dB was made as 90 degree, it was found that dB was maximum, strongest, or you can use the word maximum because anybody would be quantifying it. And if dB was made as 0, theta was 0. From here we said that dB varies proportionally with sine theta, because you know sine 0 is equal to 0, sine 90 is equal to 1. dB varies directly as sine theta. Clear? Okay. So let me mathematically write down whatever we said. We said dB is directly proportional to I, dB is directly proportional to dL, dB is inversely proportional to 1 upon R square, and dB is directly proportional to sine theta. These are clear with us? Now combining 4, okay, combining the 4 observations, you actually can say dB, just let me write and then you do. This is proportional to I dL sine theta divided by R square. So dB is equal to mu naught by 4 pi I dL sine theta by R square. You will just take off the R from the top. Observe what I am writing now. Now see, if I bring the vector, then this is mu naught upon 4 pi, okay, I. Now sine theta, theta is the angle between what? Theta is the angle between DL and R. So we will write here as dl vector into r cap, unit vector, right, divided by r square. And in books sometimes you may also find this expression as mu naught by 4 pi I dl cross, what is r? Unit vector. Unit vector is the vector stripped out by, then this will become r. So just make that small changes in r. If you remember your diagram is something like this. This was your, and this is a unit vector, okay? So this is r cap. That was r vector. The whole thing is r vector. This is just r cap, and this is dl vector. This angle is theta. Which one? Magnitude is always r square. And when we are actually, see here also it is r square. Just because I replaced the unit vector. What is a unit vector? A unit vector is the vector divided by the value of the magnitude of the vector. You remember that, right? If A is a vector, then A cap is said to be the vector A stripped out of its magnitude, which is nothing but A by A. A cap is A by A. The same funda we have used here. ठीक है? Mu naught is known as, see, you had one epsilon naught in electricity. So epsilon naught was permittivity. This is permeability of free space. This is permeability of free space. And the constant mu naught over 4 pi is equal to 10 to the power minus 7 Tesla meter over ampere, right? 10 to the power minus 7 Tesla meter over ampere. So actually, if you only see the value of mu naught, see, it is something stylish. If you see mu naught is 4 pi into 10 to the power minus 7, okay, Tesla meter per ampere, which actually shows you magnetization is very easily possible through vacuum as well as free space. This is Biot-Savart law in vector form. This is Biot-Savart's law. It gives you the strength of the magnetic field. Okay, now we're still not done. We're still not done. If I ask you now to find out, so let me go back to my previous slide. Okay, let me go back to my previous slide. So here we have found a relation now. dB is given by mu naught by 4 pi. Okay, mu naught by 4 pi I, then dl, then sine theta divided by r square. Fine, you got the magnitude. Now how do we get the direction? Right, because dB is a vector. Now when you say about dB, then you need to specify what should be the direction also. Now in order to specify the direction, we will again bring what is known as our right hand thumb rule. Right hand thumb rule. So what is my right hand thumb rule? I will always point my thumb. Look at my dl vector. I will point my thumb along the direction of the current. Right? Or else you can also say dB as a vector came out from the cross product of what? From the cross product of dl and r. Got it? So dl and r means, you know how to do cross product with your right hand thumb rule? Take your hand and position it with dl. dl cross r means move dl towards r. Move dl towards r. Where is the thumb pointing? It is going inside. Got it? And dl is what? Basically it is the current element. So if the current was going in this direction, then I would have moved dl cross r. dl cross r. This is my dl cross r. The thumb would have come outside. So here I will, for this particular diagram, I will show my symbol as this. This is the direction. Are we fine? Okay. Pretty easy. So a quick recap. A current carrying wire, and we have a point P nearby it, and a current carrying wire creates a magnetic field, behaves like a magnet. Oersted experiment. Biot-Savart law is one step ahead of it. Oersted only told us about some relations, that how the magnetic field varies with the direction of the current, with the polarity of the current. Biot-Savart law goes one step further and tells us actually the magnitude of this magnetic field, and it's an experimental derivation, which is the experiments and those things are beyond your syllabus. All you need to understand is the concept of a current element. A current element is a small section of a current carrying wire, and it is considered as a vector whose magnitude is equal to the small segment's length, and the direction is the direction of electric current at that place. The best way is to take your current element and draw a tangent along with it. That is the direction of the current element, right? And then you position your point wherever you want to find out the magnetic field, and take a displacement vector r vector, which is actually at a distance r from this, and there is an angle theta. The experimental evaluations tell us that this magnetic field will be directly proportional to I, directly proportional to dl. There is an angle dependence such that it is dependent on sine theta, means at 90 it will be maximum, and at 0 it will be 0 or minimum, and as an inverse square relationship with r. Based on all these findings, we actually combine them, and when we combine them, we arrive at dB is directly proportional to IDL. And when you remove the constant of proportionality, the constant brought is mu naught by 4 pi, where mu naught is said to be the permeability of free space. Mu naught by 4 pi overall is a value 10 to the power minus 7 Tesla meter upon ampere. Did you understand why it is Tesla meter upon ampere? DL is meter and meter square, so it becomes meter at the bottom. The meter goes here, Tesla goes here, and the current's ampere comes this side. So it is Tesla ampere upon meter. ठीक है? So our next thing would be comparison between Biot-Savart law versus Coulomb's law. So we will have comparison. So make a T structure, Coulomb's law, and on this side we will have Biot-Savart law. Coulomb's law and Biot-Savart law. So the first point of difference is this actually gives you what is known as an electric field. This will tell you all about a magnetic field. Now here the source is a charge. The source for everything is a charge Q in Coulomb's law. The source is charge Q means the source of the electric field is this. This is going to talk all about E, and this will give you the relation where magnetic field and electrical field can be correlated. And here, what is the source charge? Can you tell me? What is the source? Moving charge. Here the source is a moving charge. This we had done in last class also. It's a moving charge. This gives you electric field E. And this will give you magnetic field B. Okay, we are comparing, and just put one short note above it that this is the comparison of all similarities. We are just comparing the similarities. That will also compare the differences. 3. The electric field follows the inverse square relationship. The magnetic field also follows the inverse square relationship because we are studying all similarities. 4. This follows superposition principle. This also follows superposition principle. Means if you want to find out the net magnetic field, then you add up vector addition of all the individual magnetic field. Clear? Okay. Now let's see the differences. Let's see the differences. Number 1, this is produced by stationary charge. This is produced by moving charges. I think here then we will use what you said was better. Yeah, source is, because since we are using this in dissimilarity, source is current element. Sorry, children. Current element DL. Without DL we can't have it. Produced by stationary charge, produced by moving charge. Then our next point is, this is interesting. Electric field E is along R. Here magnetic field B is perpendicular to plane containing DL vector and R vector. It is perpendicular to the plane containing DL vector and R vector. Third, no angle dependence. And here B depends on sine theta. Sine theta. Is a long extension of current element. Which one? Coulomb's law is all in electrostatics. Moving charges exert, but moving charges concept is not brought in Coulomb's law. Coulomb's law is two charges at rest. Otherwise, how will you define R? R cannot be defined. Okay, so this angle dependence, you can add one line that if the point lies along the extension of the current element, if the point lies, okay, what we are trying to say is something like this. See, if you understand this, then it will be easy for you. Say, suppose this is I, okay, and I have taken a small current element out here. This is my current element, which is say DL, and what I'm trying to say now, see what is DL vector. If the point lies, what they're trying to say, if my P point, your P point was here, if P point lies on the extension of the current element, then the magnetic field will always be 0, because then your R will be along this direction only, or in this direction. Theta will be either 0 degree or 180 degree. So you write down, if the point lies along the extension of current element, if the point lies along the extension of the current element, then current element does not contribute to magnetic field. Then current element does not contribute to magnetic field. Current element will not contribute to magnetic field. Now, one more topic here we will add, a relation between mu naught, epsilon naught, and C. C is speed of light, okay? Relation between mu naught, epsilon naught, and C. So the relation is mu naught into epsilon naught is equal to 1 upon C. Permittivity of free space multiplied by permeability of free space is the reciprocal of speed of light. And I hope you know the value of C. C is equal to 3 into 10 to the power 8 meters per second. That is speed of light. Speed of light, or any EM wave. This is actually later used in electromagnetism also. Clear? After this, we actually have a problem, but we have one more derivation. I think we have time. Let me first finish off the derivation, then we'll go into the problem. This is all about Biot-Savart law. So mu naught by 4 pi I dl cross R divided by R square. Okay. Our next topic is magnetic field on the at a point on the axis of a current carrying loop. Same like electric field. Magnetic field at a point on the axis of a current carrying loop current carrying loop. If you understand the diagram, the whole derivation also you will understand very clearly. We have a current carrying loop. This is a current carrying loop in which the current is actually moving in this direction, anti-clockwise. Okay? This is I current which is moving. Current carrying loop, I current. O is suppose the center of the loop. R is the radius of the loop. R is the radius of the loop, and all you are interested is to find the magnetic field at a point P, and P, suppose this is the point P. This is my point P. P is at a distance x from the center of the loop. Are you understanding? Current is now moving in a loop. I want to find out what is the magnetic field at a point on the axis of the loop where the point is P and it is at a distance x from the loop. The loop has a radius of R and the current I which is flowing anti-clockwise. That anti-clockwise is not a headache as of now. And distance is x. Okay. So we are taking two current elements and the current elements are taken in this manner. See, I am taking a current element, say at this portion, if I take a current element, it will be in this manner. And right now I don't need it, but just I'm keeping, there can be a diametrically opposite current element also, just same as this. You remember in electric field also we used to take a diametrically opposite. So this is DL, this is DL. The diametrically will show its role later on. Fine. And we are going to find out, so our concept is same. We are going to break down this loop into small current elements, and DL is one such current element. And we are going to find out what is the contribution of DL for the magnetic field at P. And then if we integrate such DLs over a cyclic loop, we should be able to get the value of the magnetic field. Clear? Now, if you go by Biot-Savart's law, then what all did you take? You had a DL, then you had a distance or a displacement vector of DL to the point where you were finding out. So we need a displacement vector. So let's create that arm also, say from here till P, and this is, we are taking this value as R. See, if it was exactly a loop, no, it should not have overrun it. So this is, say, R. Fine. This is R. And one relation straight away you can take up is that R can be taken as root under x square plus r square using Pythagoras theorem. This we can find out. This is something that is already established for us. Okay? So you can write down by that time, consider a tiny portion of the loop whose length is DL, and the loop is, that DL element is at a distance R from P. Applying Pythagoras theorem, R is equal to x square plus r square, where capital R is the radius of the loop and x is the distance. Right. So we first apply Biot-Savart law. Biot-Savart's law will tell me dP is equal to mu naught by 4 pi I dl sine theta divided by r square. This is the standard form of Biot-Savart's law. And if I want to bring it in vector form, then I would write that dB is equal to mu naught by 4 pi I dl cross r cap I am writing, okay, divided by r square. Is this thing fine? R cap, and r cap can be taken as r cube. Okay. Okay, write down. Current element DL, current element DL as a current element is always perpendicular to R. Current element DL, sorry, not this R, is always perpendicular to the R vector. Just try and see. R, this is a loop. You have to link it like 3D. Imagine my hand as the loop, and this is the point. This is R. The loop is running this way, so the DLs will always be like this. And this is R. So wherever you actually take a DL, from there the R will come up. So the DL will be always perpendicular to R. Are you able to visualize that or not? My hand is a loop. Imagine my hand is a loop. Look here, my palm is a loop. And this is the axis of the loop. Right? This is the loop with the axis. R is this one. R is the top portion when you are taking DL. Now DL will make a 90-degree with this R. Sir, you take DL here. Very good, take DL here. Then in that case, if it is anti-clockwise, DL is moving upwards, R is from here. R and DL will always be perpendicular. Are you able to appreciate that? Which means, in this case, theta will be equal to 90-degree and sine theta's value will be equal to 1. Sine theta's value will be equal to 1. Therefore, dB can be now set to be mu naught by 4 pi I dl divided by r square. Mu naught by 4 pi I dl divided by r square. And further, I can write it as mu naught by 4 pi I dl divided by x square plus r square. Check. R square. You can put your note out here that R is equal to root R square plus this. We'll put that. Now is interesting thing, okay? Now you have found that there is a magnetic field at P. You have found that there is a magnetic field. Now what is the direction of the magnetic field? The direction of the magnetic field is perpendicular to a plane containing DL and R. Right? If this is a loop, the loop is like this. Look, the loop is like this. So the DL is coming out of the board. Got it? The R is going right from the board till the down portion. So both are on, say if I take this as X plane and this is as Y plane, both are on XY plane, then DB should be on Z plane. That means DB should be moving 90-degree opposite. See, this is one plane, this is one plane. So the DB will be actually moving this way or this way. It will not be DB will not be along the direction of the axis. DB will be something like this. Z axis. Actually, the diagram should be such that this DL and the Z axis, the thing is that otherwise it becomes difficult to understand. So I just made it too much slanted because there's one more thing which will haunt you now. Wait, after this. DB will be almost, in this 2D view, you will see this parallel to this almost. This is coming out this way, that will go out that way. You'll see them as parallel. So this is my DB. So you can write down a line, write down the magnetic field DB due to one current element, just write one current element. The magnetic field DB due to one current element is not along the axis. Is not along the axis. It makes an angle theta. So it will make an angle theta out here. It will make an angle theta out here. Got it? If it makes an angle theta, then you should be able to resolve it into its perpendicular as well as its horizontal components. Perpendicular and horizontal components, you can call this as dB perpendicular component, and this is dB x component. dB perpendicular and dB x. Huh? You want to increase it? Huh? What happened? You can switch on that fan. That will blow, give you more comfort. Bottom. Okay. So to which you will write 1 minute, huh? Otherwise this will create more noise. You can write the axial component. The axial component, 1 is the fastest switch actually, 3 is the slowest. The axial component is dBx and the perpendicular component is dB perpendicular or dBy also, whatever you can write, dBy or dB perpendicular. Okay. Now see the idea. When you see two perpendicular, now this one will come into role. Two perpendicular current elements will actually nullify the perpendicular components. If you take this component, then you will get a dB on this side. So it will nullify the perpendicular components and only the horizontal components will remain. So write down two opposite current elements eliminate dB perpendicular. You can write that in bracket equal and opposite. And only dBx survives. And only dBx survives. Two perpendicular current elements eliminate dB perpendicular as equal and opposite. We had the same analogy when we were doing electric field at the axis due to a current carrying loop. And only dBx survives. And you very well know that dBx should be equal to dB cos theta. dB cos theta. Now, if we apply geometry, this angle is theta. Look, theta is theta. This angle will also come theta. The idea is this is 90 degree. Theta plus 1 plus this is 90. Okay. Again, if you see this is the entire angle is like exterior angle for these two angles. This is 90, and let's see if you actually put some 1 out here, this entire thing is theta. And if you see on this side, this is 90. If you put this as 1 and if you put this as 2 and you just do two equations, you will find this is theta, this will also be theta. So cos of theta will be equal to adjacent side, which is r, divided by r. So this is r x square plus r square to the power half or root, whatever you can write. I hope till this much is okay. See, DL and R is also 90 degree. Children, I may not be able to, I might have not have been able to draw it properly. DL and R is 90 degree. That's what you have already assumed. This will always be 90. And this angle will be equal to theta. So can you now find out what is the value of, let's say, what is the value of dBx? So dBx can be now written as mu naught by 4 pi I dl. Sin theta's value was 1, so we have to bring cos theta, which is an r, and this was x square plus r square, and this is x square plus r square, so it becomes x square plus r square to the power 3 by 2. Just check. X square plus r square to the power 3 by 2. Okay. I'm just changing the screen. I have to, but I'm still writing the expression. dBx is equal to dB cos theta, which is equal to mu naught by 4 pi I dl x square plus r square multiplied by cos theta, and cos theta is as I said r divided by small r, which is x square plus r square to the power half. This was our expression, right? So if you combine this expression, you get mu naught, and then you have a I, and then you have a dl, you have a 4 pi, and on this side we will have a r, and we have x square plus r square to the power 3 by 2. Fine. Now if you see in this expression, mu naught I r, a steady current is flowing through the loop, r is fixed, 4 pi is fixed, the point at which you are measuring, that is also fixed, r square is also fixed, and 3 by 2 is a constant. Everything is constant, and only the dl is something that is variable. This whole term is constant. So the entire magnetic field B will be equal to this factor, closed surface integral dl, closed surface integral dl. Okay? Which means B should be equal to mu naught I r by 4 pi x square plus r square to the power 3 by 2 multiplied by 2 pi r. If you integrate dl over the entire loop, you will get what? Circumference 2 pi r. So pi cancels pi, and the r and r makes it an r square. So your B's value is equal to mu naught I r square divided by 2 x square plus r square to the power 3 by 2. Clear? On this basis, magnetic field B at center of loop. Now in center of loop, what happens? X value will be equal to 0, because x was the point, remember? Just see, if you try to find out at the center of the loop out here, then x becomes 0. So if x becomes 0, then your expression becomes B is equal to mu naught I r square 2, this will become r cube, square takes away this, so it becomes mu naught I by 2r. This is a special expression when at the center. But hang on, we still need to find out direction of, for that current element dB, what was our direction? We need to still find out dB. Okay. So we'll go back here. See how to find out dB's current. This is interesting. You found dB here, but finally, which was the component? dB cos theta was the component, right? dB cos theta. That is, dBx was the, dB was our magnetic field. We split it into its vectors, then dB is gone. The perpendiculars are eliminated, is dBx. Now see, my loop is like this, right hand thumb rule. Curl your fingers the way the current is going. The current is going in this direction. Current is going in this direction. So I curl my fingers in this way. Look where my thumb is showing magnetic fields. So it is shown by the right hand thumb rule. It is shown by right hand thumb rule. And if the current was going anti-clockwise, just see, if the current was going anti-clockwise, then it would have gone this way. Clear? Yeah, sure. It's easy derivation, both of them. Based on Biot-Savart's law, just one minute, we have one problem. I have some time, we can do that. Can I go ahead, children? Ajay, I hope you are aware of this is, though this is vector geometry, but still, if you don't know this, you'll not be able to do the problem. These are my three axes, okay? And say suppose I have drawn the unit vectors, then what is this unit vector? I along the x-axis, j is my unit vector along y-axis, and k is my unit vector along z-axis. Always remember it in this manner. This is, say, I, j, and k. I, j, k. And you suppose have to find out cross products. What is I cross j? Just simple in mathematics. I cross j. So I cross j means 1 multiplied by 1 into sine of the angle between the two. So that is also sine 90, which is 1. But question comes is, what is the direction, right? I cross j. So let us think. I, we have to move towards j. So it is actually taking my positive z direction, but that will be represented by its unit vector. So I cross j gives you what better? I cross j actually gives you k, right? Let us see now j cross k. Now the best way to remember is I cross j. We always move in a circular manner. I cross j, k. I cross j, k. J cross k, I. And then k cross I will give you j. But if you move ulta, I cross k, then it will be negative j. Have you understood the logic? So let's see. You know this, k cross I. Look just here, k cross I. What should be k cross I? J cap. But you know that this is not commutative. So if you do I cross k, it has to be negative j cap. Ulta. A cross B is equal to negative of B cross A. This we use in vector algebra. Remember this so that then only this problem becomes easy for us. And this is based on Biot-Savart's law. Very easy problem. It says that you have a current element delta L, and this is equal to delta X I cap. Did you understand what does it mean? Means your current element is along which direction? X axis. Delta X I cap, and the figure is also drawn. So let's draw the figure. So we have a current element, and the current element is here. This is your current element, and the length of this current element is how much? The length of this current element is delta X. But since this is a vector, so delta cross I means current is going in which direction, children? Current is going along the x-axis in this direction. This is my delta L. It's a vector. Okay, is placed at the origin and carries a large current, the value of the current is 10 amperes, huge current. Okay, 10 amperes. What is the magnetic field on the y-axis at a distance 0.5? Magnetic field on the y-axis, so you need to find out the magnetic field at the point y-axis, and the distance is how much from here to here? The distance is 0.5 meters. Okay, and delta x, the delta x length is 1 centimeter, which is equal to 0.01 meter. Clear? So you need to find out the magnetic field at which point? The magnetic field at this point on the y-axis. Come back to Biot-Savart's law. What does Biot-Savart's law tell you? dB is equal to how much? Tell me. dB is equal to mu naught by 4 pi I dl sine theta divided by r square. The value of sine theta in this case will be how much? 90 degree. So it's equal to 1. Mu naught by 4 pi, I can assume. What is mu naught by 4 pi? Mu naught by 4 pi is 10 to the power minus 7. What is the value of I? 10 amperes. What is the length of the current element dl? 0.01. So 1 into 10 to the power minus 2. Sine theta is 1. And what is the value of r square? It is 0.5. So it is 5 into 10 to the power minus 1 and square. So 5 into 10 to the power minus 1. This should be. Shall we calculate this quickly? So let's calculate. Let's take the care of all tens first. 10 to the power minus 7 and minus 2 is minus 9. Minus 9 plus 1 is minus 8. Minus 8 plus 1 is minus 7. Minus 7 plus 1 is minus 6. Minus 6 divided by 1 by 5 into 5, which is 1 by 25. 10 to the power minus 6, 1 by 25. Right? How will you do this? 1 by 25? 4 into, this is equal to 100. So if this was 100, then 25 makes it how much? 4. But this is not 100. So this is 4 into 10 to the power minus 2 into 10 to the power minus 6. ठीक ना? So this should be 4 into 10 to the power minus 8. Magnetic field we are finding out. So 4 into 10 to the power minus 8 Tesla is exactly correct. Now tell me what will be the direction. Use your common sense. What is the direction? No. Here don't put hands. Here direction is simple. The r unit vector. Now this is here. What is the unit vector you are playing with? I cap. And the r is with the unit vector what? J cap. Oh, this is with J cap. Have you understood? It is dl cross r. Means I cross j. I cross j is what? K. So that means the direction will be, direction is along positive z axis, or you can say k cap. This is how we find it out. Positive z axis, which is k cap. Clear? Biot-Savart's law, you need not put right hand thumb rule. Biot-Savart's law, you just put dl cross r. The vector is not r cross dl, dl cross r. Because see, sir, if I would have done r cross dl, then r cross dl means you would have done I cross j, dl cross r. So r cross dl means you would have done j cross I. J cross I will give you negative k, which is wrong. Okay? So just like you had Gauss theorem, now we will come to Ampere's circuital law. That is for magnetism's Gauss theorem. Okay? Which we will do in our next class.